Lite kort om projektet då. Den formella titeln på projektet som vi kommer att höra resultat från idag heter Svavelfritt ligninbaserat marinbränsle. Det är Dimitris, jag kan knappt uttala hans efternamn, ursäkta mig, Antanasiadis kanske, från SLU som har varit projektledare. Och sen har då David från SLU och med flera från LTU och SSPA och Lunds universitet deltagit i projektet. Projektet avslutades nu nyligt här i april och budgeten har varit någonstans 2,3 miljoner ungefär. Och ni kan hämta leveranser ifrån projektet på projektets webbplats som det finns en länk till här också. So with that I'll turn to English and I say please go ahead David to share your presentation. I will stop mine and very welcome here today and I'm curious to hear more about your results.
Thank you very much. I hope you can hear me all right and see my presentation.
Yeah. Yes, everything works fine here.
Excellent. So I will be speaking about the project today, sulfur-free renewable marine fuels, and that's through organosolv lignin extraction. My name is David A Agar. I'm associate professor at the Department of Forest Biomaterials and Technology, and that's at SLU in Umeå. My own research is more focused on solid biofuels and thermal treatment, mostly in energy applications. But today I'll be presenting this project on behalf of Dimitris, who wasn't able to present today. So the outline is very brief. I would just give the overview of the project, and then I'll jump right into the key findings that come out of the project, and then maybe discuss some of the background and slightly more details on methods and results, but nothing in too much of detail. For that, I will leave for the question period following the presentation, where some of the partners are in the audience here today on the webinar. So the project in general, it wants to investigate a renewable biofuel option to replace fossil marine fuels. And it does that by demonstrating, it wants to demonstrate production of such a lignin-based fuel, and we call it lignin, the fuel. And the production is carried out at Luleå Technical University, and it involves using lignin derived from forest-based biomass, wood, using this sort of novel organosolv pre-treatment method. The lignin, which is then extracted from the biomass, can be blended with, in this case, ethylene glycol, and then the mixture, the blend, is the finished biofuel. Now, in the project, ethylene glycol, it was actually used commercially, a commercial available one, but in sort of a real life application of this process, then the glycol itself could be co-produced using fermentation of the other wood component, cellulose. You can see here that the separation from the wood, the cellulose and lignin parts, can recombine then to form the liquid biofuel in the kind of ideal application case. Then the fuel, the objective was to combust the fuel in an experimental engine at Lund University and analyze how that performance went. And then also the costing of production and costing of such a solution was taken into account from SPA Gothenburg. So to look at the market potential for such a fuel and the economics of production in Sweden from biomass. Finally, then a life cycle assessment, which is carried out at SLU, looks at the environmental footprint of the whole process and how does it measure up in a way. So I hope if we have detailed questions, we can return to those after my presentation. So there's a spoiler alert now. The key findings were that the fractionation process, the organosolv fractionation process, was successfully demonstrated for a renewable biofuel. That fuel had a heating value, so effective heating value of about almost 19 megajoules per kilogram, and that if you compare to fossil-based heavy fuel oil, it's an energy density of about half. So it would require sort of a doubling of fuel tanks or shorter trips if it was going to be used in practice. That may not be an issue for certain routes. Production costs, they came out at about, from this Swedish production scenario that was analyzed, they came out at about 37 euro cents per liter. And it's important to say that is without taxes, without labor and subsidies. So that's really a minimal cost for production. And then combustion was successfully carried out at Lund, and the fuel in this particular setup of engine, which we'll maybe come back to later, it showed relatively normal performance at low loads. So and the last key finding was, and maybe from a policy perspective, the most important, is that the LCA, the life cycle assessment, showed that the lignin production has a low environmental impact. So that's the good green side of the news. We all are familiar with the climate policy, with the energy policy in the EU. It has two main objectives. Number one is to cut emissions of greenhouse gas, and the second is to secure more inland sources of energy. Now, those are in the toolbox. Those are achieved with setting targets, and then the next upcoming target is the 2030 target, where we're looking to cut 40% emissions, mostly through raising the amount of renewables that we use. And this also ties into the more recent European Green Deal, which has a longer forecasted objective, and that's climate neutrality in the EU by 2050. So these are huge plans, and of course they're very expensive, something of the order of 260 billion euros per year until 2030 to carry out those tasks. So it's really about what are the best sources to achieve, what's the best cost of achieving these targets. And we've heard a lot in the media in the last few months because of the war in Ukraine, the importance of energy importance. So if you look at the EU, and particularly not for all their fuels actually, but in this case the orange line, which is just their crude oil imports, which is where marine fuels are derived from, you see that the dependency is about 90% at present, and most of the supplying countries are seen here. So it's really has become a hot topic, and it really highlights the importance of why the EU has selected inland production as one of their main pillars of their energy policy. it's derived from this kind of figure. So heavy fuel oil is a residual fuel oil is a remnant product from petroleum distillation. It presents a lot of environmental risks, like from spills. It can contain toxic compounds, and combustion can lead to particulate matter, all kind of bad, dangerous things. And it accounts for about 5% of the products from petroleum distillation. And because it's the heavier option, so the lighter fuels, they are tapped off the distillation higher up in the column. But the fuel oil, because you get a lot more heavy substances, not as heavy as the bitumen, which is used in asphalt, for example, but you get a lot of inorganic compounds that you might not want. So that's kind of where it's coming from, and why, in a way, it's been traditionally quite a cheap fuel, and important to raise the standard of living, of course, globally over the last several decades. It's important to point that out as well. And it's not just one product like a wine or a coffee. It comes in different grades. This is just an old example of the grading system of heavy fuel oil. So it's the constituents depend very much on the origin of the petroleum and the refining process. But let's look now at the global fleet. So about 100,000 vessels are currently moving around in the oceans of 100 gross tons or more. And of course, there are regulations in place already that looks to ban fuels with high sulfur contents. So the UN IMO has had a ban in place since 2020, looking at limits of 0.5% sulfur content. And then there are also emission control areas such as the North Sea and in the Baltic, which further restrict sulfur in fuels to 0.1%. And like other sectors, greenhouse gas targets are desirable. So the IMO is looking for 50% reduction by 2050, and the Swedish Ship Owners Association net zero emissions by 2050. So what do we have to think about when we replace heavy fuel oil? There's a lot of factors that come into it. Of course, there's security of supply. There's the economic factor, which is important, and then there's a technical factor, whether the fuels can be used in existing engines, or should there be retrofitting of the engines, for example, and then of course environmental impact of the fuels, and do they sync up with our future goals. There are some options already available on how to use low sulfur fuels that fit the regulations. There's the drop-in fuels, which I mentioned, that don't require retrofitting. There's some examples here. Then there's alternate fuels that do require retrofitting. Some of them are not technically developed yet. And then there's also kind of an old school cleaning of the emissions, scrubbing emissions and using the same fuels. But of course, that doesn't eliminate the fossil content of the CO2 emissions. So lignin is a source in the project that is looked at for production of fuel. And of course, we all know, we've heard of lignin. It's one of the three main components of woody biomass. It's a supporting tissue in trees and plants, and it's very important already in production of things like wood pellets and particle board where it has a kind of a gluing effect because of its softening and rehardening at higher temperature and pressure. So wood contains between 23 and 29% lignin, and that's the lignin is very difficult to isolate from wood, and it's for that reason they call lignin that's isolated from wood technical lignin often. The biggest source of technical lignin that we have is from the pulp and paper industry. So kraft lignin, which is used usually in recovery boilers to get energy back in the pulping process. That's one of the main uses, but unfortunately has sulfur. So sulfur-free lignin types, there are a few options to produce sulfur-free lignin, and the organosolv process is one of them. So now I'm just going to go through some of the methods that were carried out in the project, and in a very general sort of way. So the organosolv lignin isolation is on the left here. Basically, there's chemical fractionation, pressing, and then solid liquid physical separation of solid liquid, and you end up with the lignin itself. And as I mentioned, then the lignin can be blended. In this case, it's blended with ethylene glycol to get the final lignin fuel. For our project, there were different weight concentrations of lignin and ethylene glycol tested, and there was a use of a catalyst, for example, and no catalyst to produce different types, different blends, and we measured the heating value of those blends. And then one blend was selected for the combustion tests. And here is an image of the combustion engine at Lund University, and this particular one is modified to operate in what they call the homogeneous charge compression ignition mode for this fuel. The biomass supply was evaluated for a kind of case study, that if we had production in Sweden at 3 ports, so in Umeå, in Gävle, and in Göteborg ports, then we could model the costs quite accurately of the forest biomass used to make the fuel. In this case, logging residues and mill byproducts. And you can see that on the x-axis here, as the amount of biomass needed for the process increases, the cost of that material increases, and that's because we have to go further from those cities, further to gather more material. So there's more transport costs to get the material back to the port. So, and the same effect for the sawmill byproducts. So. If we look at the modeled cost of production, the estimated costs of production, all the contributors of that are given here in this table. It's good to point out that the largest cost is actually from the ethylene glycol blended with the fuel. But again, that's because this was commercially ready product. And determined the environmental impact of the production. Then life cycle assessment was used. And if you're not familiar with that, it's really just a way of getting the footprint of the whole process. So in this figure, it's broken down into 3 sub-processes. So the acquisition of the biomass, the actual production of the fuel, and then the combustion and use of the blended fuel in marine engine. So these are aspects that were taken into account in the LCA analysis. And LCA is carried out in a specialized software called SEMA Pro. And available to that software, there's a lot of databases. And of course, it's a standardized method. So it's quite a powerful tool to look at different stages of production and highlights really what are the hot stages, where does most of this environmental impact come from. And then the case study I mentioned from the economic analysis, it looked at comparing costs, environmental impacts, and operational impacts for two case vessels. And those case vessels were assumed to operate in the Baltic and North Sea region, where the sulfur emissions are limited to 0.1%. And then to give a perspective of the LNG fuel, and then there's a comparison between two other fuels, one of them fossil-based, which is ultra-low sulfur fuel oil, and then a hydrogenated vegetable oil, HVO, here. So there's three columns for the three fuel types in each case vessel here. And just looking at the results, I mean, it looked at a certain operation and a certain route for shipping in the Baltic and North Sea region, and then it calculated the yearly consumption, the yearly emissions, and yearly fuel cost and such. You can see from the bolded numbers here that in both cases, both vessel cases, the fuel costs for the projected fuel costs for the LNG fuels comes in somewhere between the two other fuels. So slightly more than the fossil-based and half the price of the other biofuel, which is the hydrogenated vegetable oil-based fuel. And then interesting, the emissions, the well-to-tank tons of CO2 per year produced, yeah, they look very similar to the fossil-based system, and that's really that really comes down to this footnote here, and that's that the ethylene glycol that we used in the blend, because that was fossil-based itself, it accounts for most of those emissions. So 95% of the emission of that footprint comes from the use of ethylene glycol, which would be then could be eliminated if the glycol was produced using a sustainable process with the other fraction of the biomass. What is the impact then? So life cycle assessment produces results for different impact categories. And here on the left, you can see there's some 6 categories for this analysis. And really the only really significant impacts were in the first and last category, the global warming potential and depletion of fossil resource category. And most of those, and this mirrors the previous slide with the case of ethylene glycol, that most of the LCA, most of the environmental impact comes from that fossil-based glycol. So in a similar way, that these numbers would be much less if the glycol itself were produced in a sustainable way and not based on a fossil product. So what kind of conclusions can we draw from this project, which is really a very thin slice of a huge field in biofuels? Well, these are quite general, and I hope we can discuss some of them after my presentation, but really there's still an overwhelming reliance on heavy fuel oil, hence the targets that we've set. But that presents a big potential, and of course also a challenge to shift to new fuels. One path option then has been covered in the project, and like I said, it's a narrow slice of all potential pathways, but it's been demonstrated at least that this is something that can be done. And the Swedish biomass, for the case of Sweden, where such large resources are available from forest products, it really provides that inland production and, of course, energy security, not just for Sweden, but for other member states in the market. So that's very positive. Lastly, from a more holistic perspective, then we really need to have a cost-benefit analysis of all the options, of all the different pathways to achieve emission and sulfur targets, and then look at what is the best one for every euro spent, what is the most bang for the buck, so to say. And that's something that I hope some of the results in this project can contribute to. So I thank you for your attention, and at this time I of course not acknowledge my project partners. And you might think, why wasn't I mentioned in the project? Well, I actually joined the project at the end, and I've just really been working with compiling some of the reporting. So I look forward to your questions and discussion now. Thank you.
Thank you very much, David, for an interesting presentation. So the floor is open. If someone wants to ask a question, just raise your hand and or write in the chat. While we're waiting, if there are some questions, my first question is connected to what you talked here in the end. As you say, there are several different pathways, but if you have sawmill residues or forest residues, and you want to produce a fuel or a biofuel for the marine sector, why would you choose this lignin fuel? What are the main advantages with this pathway compared to other pathways like gasification to methanol production? Or there are several different options.
I will say something about it. I think I mean, I haven't been in the project the whole 2 years, so but from my perspective, I think what the ability to get that sulfur-free lignin. So if you're looking for lignin as a potential source, then it's very attractive because it is low in sulfur, this process. And the other thing that is implicitly assumed in that is then that it's not a standalone process that you would just use the lignin from biomass and toss the rest. It depends on integration. And in a time when we are integrating so many processes to try to maximize circular economy and the bioeconomy, and to add value to bio-based chemicals and materials and products, mostly from the forest, then it really depends on that sort of integration, I would say. Maybe my partners would like to add something.
Yes, Joanne, please. You could turn on your camera if you want.
Yes, thank you. I hope this works. Having a few connection issues. I hope you can hear me. Yes, I would just like to add to the answer by David. And you mentioned specifically methanol, and I have also worked on, and I'm working on methanol projects, which is also a good use of the forest residuals. But the difference and benefit for this one is it's more of a drop-in that could be used in the existing fuel tanks on the vessel, and with the engine without as much modification as might be needed for the methanol. So that was sort of the difference for this one, because a lot of the vessels out there sailing might be quite old vessels that might not have a shorter life to be able to sort of pay back the investment. And so if there can be some fuels that can work without modifications to their tanks, because it's quite similar to the fuel oil that they're using now, whereas methanol, although also a very good fuel, requires some additional adjustments to be made on board. So maybe would be considered more for a brand new vessel or something with a longer life.
And also, but when it comes to the sulfur content, I assume that methanol produced from different sort of biomass would have the low sulfur content as well.
Yes, that's correct.
Yeah.
Yes, yeah. It has a similar.
How does it compare with when it comes to heating value?
There it is also very similar. Methanol is about 20, so they're almost identical in that range, in that a ship operator would have to choose to put some larger tanks on board or else bunker more frequently. So perhaps now if they bunker once a month, they load fuel on once a month, and they would have to go for every 2 weeks or similar. Yeah, so they're very, very similar in that regard.
Thank you. So if someone has a question, just Monica, you're welcome. Go ahead.
Yes, hello. Thank you for a very nice presentation. I was just wondering about the engine result, and was there a reason why you operated the engine in HCCI mode, or was it just occasional?
There was a reason. I think I would direct the question to Martin.
Yeah, I should answer that question. We were thinking forth and back if we should use a regular diesel engine or an HCCI engine, because it's such a new fuel blend here. So we ended up deciding to use the HCCI process because it's better to isolate the combustion characteristics. So yeah, that's where we ended up, and we were also a bit concerned about clogging in fuel injectors and so on. We're using a high pressure fuel injection system, but of course it's a compromise. It's not ideal, but we did learn a number of things about combustion characteristics using this engine setup. The CFR engine is commonly used in oil companies to determine the characteristics of different fuels, so it also makes sense from that perspective.
Okay, thank you.
Yeah, to continue on this, I don't know enough when it comes to engines and stuff, but so this fuel, could it be used for road transport instead, like in engines that we have in cars or trucks and so on, or is this fuel that sort of kind that only works in these bigger engines in the marine sector?
So I could answer that as well, and I think it's if you would need to do a modification or certification test for a fuel for, let's say, passenger car, that is very expensive and complicated to do. I don't say it's very easy to do that on marine vessels either, but it's a much more limited number of engines and fuel tanks and so forth we're talking about. So I think it would be very difficult to start to introduce it on the passenger car market, for instance.
But technically it would work. It's more the process around it, or
we would have to do a lot of testing and certification testing to actually verify that it would work in all different conditions, and especially with emission after treatment systems. the regulations on road are very strict, and it's a lot of different devices that need to work with the engine and the fuel.
Okay.
Can I add hook a question here from Monica's side here?
Go.
I was just wondering, is it far away from the EN 590 standard, this fuel, or is it relatively close?
The results we have indicates it's very far away from EN 590.
Okay. No further questions.
Then I had another question regarding the actual organosolv process. Now it's been some years since I worked more in this field, but like 15-20 years ago when we talked about organosolv processes, then it was an issue with the solvent and how you could do recycling and reuse and get the sort of cost and environmental aspects of the actual organosolv processes that were discussed back then. How have you any comments on this?
Unfortunately, I'm not familiar with the process at all. Leonidas, who I'm not sure is here. I don't think he is.
No, I don't think he was.
He is the specialist in this process. So I would also like to hear the response to that question.
Okay, then we just have to what you say, put that question aside. So, but have you planned any further work? How will you continue this project in any way?
Yeah, that's a very good question, and it definitely. I know from our perspective, I can say that the results will be used and present new pathways and new options for other projects that we have in parallel. So I don't have a specific answer how the results will be used, but they definitely will be used by us. By us at SLU, they will be used quite a lot, and I'm sure the other partners have a similar response that they will the results to have definite value for their work.
But there are no plans for upscaling of the process to produce more of this LINEG for further testing or so?
I can't answer on behalf of Dimitris, or Leonidas, but perhaps one of the other partners knows what's in the works with regard to that.
Martin turned on his camera, so maybe he has something to add.
Yeah, I would like to add something there. So, I mean, considering the potential great values of lignin-based fuels, we for sure are very interested to continue on understanding more on the combustion quality of lignin-based fuels or blends, and we plan to continue to work on that. We have discussions with other project partners and on how to continue that work, but it's nothing decided yet, so we see where it takes us, but very interesting.
Yeah. Good. Do we have any more questions from the audience here? It's quiet. Then even if we have plenty of time, if there are no questions, I think the questions I had we have discussed. So maybe we can wrap it up if I give you some more seconds to ask your question or raise your hand if you have a question. Okay, then I say thank you, David, very much for an interesting presentation, and your co-authors here who answered and made interesting addition to the discussion. So thank you very much for today, and
thank you. It was a pleasure.
Yeah. Bye.
Goodbye.